Hi, it's Brenda Davison speaking, continuing on with the lectures for Math 152, Simon Fraser University, spring of 2020. I recognize that there's a watermark on these videos here. I will maybe attempt to get rid of that. We're just trying to get up and running quickly, and I think if you could just probably learn to overlook that just for these first couple of videos of mine, I will attempt to fix that problem as soon as I can. Okay, let's take a look right now, section 11.3, the integral test and estimates of sums. So basically the idea is we're going to use when we're looking at a sum, like this thing here, from 1 to infinity of some function defined on the positive integers, what we're going to do is compare that with the equivalent integral defined on the positive real numbers. Okay, so for example, we could take a look at this sum that is listed here, the sum of the reciprocals of the squares. This is a extremely interesting problem. It's called the Basel problem, and it is asking what is the sum of the reciprocal of the square numbers. I find this result absolutely astounding. Unfortunately, we're not going to be able to show you, or we're going to show you in this lecture that, well, most certainly this converges. So it does equal to some number when you add up all infinite of all of the sums of the reciprocal of the squares going all the way to infinity. It definitely converges. We'll show that. But what it converges to is actually a more difficult problem. And if I have time in the next week or so, I will post a little blurb about article about how you can figure out what it converges to, because this was posed as a problem, and the answer was not known. And Euler took this problem on, and being a very clever fellow, he did manage, using the zeros of the sine function. Just think about that. Using the zeros of the sine function, he managed to show that this sum indeed converges. And it converges to this number here, pi squared over 6. Okay, so what we're going to do here is just try to use the integrals to determine whether or not the sums converge or diverge. Okay, so here we are. What do we know? We've got a drawing here of the function y equals 1 over x squared. And let's just take a look at this sum here represented graphically. So I'm going to draw a little box here like that. And the area, well, that's the length times the width here. So the area right here is 1 over 1 squared. Okay, and then I draw a box here like that, and I see what is the width. The width is always going to be 1, and then the height, well, the height is in fact this number right here is 1 over 2 squared. So this point right here is the point 2, 1 over 2 squared. I know that because it's on the curve, on this curve defined by y equals 1 over x squared. Similarly, I know what this point is here. It's 1 over 1 squared, and this point similarly here would be 3, 1 over 3 squared. So I can calculate the area of each one of these rectangles. I'm going to calculate the area of that rectangle, of this rectangle, of this rectangle. Okay, and I have this area here. The area there was 1 over 1 squared. The area here, width is still 1. Height is now 1 over 2 squared. So width times height, the area is 1 over 2 squared. Here the area is 1 over 3 squared, etc., etc. So in fact, each one of these terms up here is represented by one of these areas here. Now, how about I exclude this first rectangle for now? I'm just going to exclude this guy. Forget about that. Let's just take a look at this curve coming right here, starting at 1 and continuing to infinity. It's pretty clear that whatever the area under that curve is, let us ask, what is the area under that curve? If I start here in the red and I go here, what is the area under that curve? Well, that would be the area from 1 to infinity of 1 over x squared dx. That is the area underneath the curve. Now, that is clearly larger than the sum of all the rectangles that lie underneath of it. So if I consider this rectangle and then this rectangle, and then I would have to go kind of small here on this rectangle, but I get the next one here, and I keep doing that. Clearly the area under the integral is more than the area under, if I add up the area of all those rectangles. Okay, so that's where I'm going here. So then, in fact, if I could show, it doesn't matter. This is a finite number. So if I can show that this integral here from one to this one here from 1 to infinity of 1 over x squared dx converges, then the sum of those numbers under there must also converge. Okay, so that's my idea. Meanwhile, we know how to evaluate this improper integral. That is the limit as t goes to infinity of 1 to t of 1 over x squared dx. And then we do the integration and we get the limit as t goes to infinity, and the integral of 1 over x squared is minus 1 over x, and we're going to evaluate that at 1 and t, and then that is the limit as t goes to infinity of minus 1 over t plus 1 over 1, and that is equal to 1. So we have that integral is 1. The integral from 1 to infinity of 1 over x squared dx is equal to 1. Okay, what does that mean? That we would have then that 1 plus the integral from 1 to infinity of dx over x squared is equal to 2. I mean, all I did is take this thing and add 1 to both sides. Okay, now this thing is here, and that is this that I'm going to line up with this rectangle right here, and the rest of this thing is less than this thing. I'll write that out. So this 2 must then be greater than or equal, no, sorry, greater than the sum as n goes from 1 to infinity of 1 over n squared. So it is bounded above. Okay. So by this mechanism of using the integral, cleverly, I have managed to show that this sum is bounded above. It's bounded above. It's the partial sums are increasing. Partial sums are increasing. How do I know that? Every term is positive. So each time we take another additional term in the partial sum, it has to get bigger because all of the terms are positive. Because, oops, let's try that again. Because every term is positive. Okay. What do we know? We had a theorem earlier on. Something is bounded above and increasing. I mean, in this example, it's not the sequence of numbers that's increasing, but it's the partial sums that are increasing. So and they're bounded above. So therefore, we know it converges. Okay. So what have we showed? Bounded above and partial sums are increasing. We have a theorem that then guarantees us that this thing converges. Again, the idea of converges to what can sometimes be extraordinarily difficult to answer. In this case, this was a famous problem, and it took a fair bit of time for somebody to figure that out, and it does converge. We do know what it converges to, but this is in general not a non-trivial problem to figure out what they converge to. Okay, so let us just compare another integral with another infinite series. Okay, this infinite series, let me write out what the terms look like. They look like this: 1 plus a half, plus a third, plus a quarter, plus dot, dot, dot. This infinite series has a name. This is called the harmonic series. I'm going to tell you right now, we're going to see the result come, but I'm going to tell you right now that it diverges. This is an important line in the sand. You must be clear that this series diverges. Okay. So, and the classic sort of problem when thinking about this is to say, hey, like these things are getting smaller, and in fact they're going to zero. Like, for example, it is true that the limit as n goes to infinity of 1 over n equals 0. So the terms get arbitrarily small, but that is not enough. That is not enough to make the series converge. So it is a necessary condition. If the terms didn't go to zero, for sure it won't converge. But even when the terms go to zero, it may be the case that the series diverges. So you have to be very, very careful not to make the mistake of noticing this and then potentially incorrectly concluding that the series converges. It does not. In this case, it does not. This is the harmonic series. It diverges. I'm going to harp on this every time that I give one of these lectures. I will advocate for asking this question on the final exam. Here it is. This series here, converge or diverge. Please answer diverge. And you know, if I see you 5 years down the road and you recognize me as your Calculus 2 instructor, I definitely want you to come up and tell me what you're doing and what kind of job you have or where you're studying in graduate school or whatever it is that you're doing. I'm always curious about that. However, if you acknowledge that you're my Calculus 2 student, I will ask you, even 5 years down the road, 10 years down the road, the harmonic series, does it converge or does it diverge? If you can't remember, hide, cross the street and avoid me. Okay, it's really important to remember this one. Okay, so let's take a look at it. We're going to compare the integral from 1 to infinity of 1 over x with the infinite series from 1 to infinity of 1 over n. Okay, here is a picture of the function y equals 1 over x. Let us take a look at this rectangle right here. Okay, that has area 1. This point right here is 1, 1. And then let us take a look at the next rectangle, this one here. So this area here, I was put A for area. The area equals 1. And then this area here, well, this point right here is 2 and a half. Fix that. 2 and a half. Okay, so the area here is a half. And then similarly, we have this point here, and we're going to draw a rectangle around that. And then we're going to look at that point right there. That point is 3, and the y coordinate is 1/3. Okay, so each one of these rectangles has width 1, and then they have heights 1, a half, a third. So basically our areas are exactly those terms from our infinite series. Okay, just not worry about what happens in the area in the this part of the graph here before what it doesn't matter. We're not worried about that at all. Let us just look at what happens after x equals to 1. Okay, what do we know? We've already shown that the integral from 1 to infinity of dx over x diverges. Right? It diverges. We can integrate that, and we know that in fact that well, let us just integrate it so that we can remind ourselves of this. The integral from 1 to infinity of dx over x, that is equal to the limit as t goes to infinity of log t minus log 1. Okay, that's where I change this upper bound to t and take the limit as t goes to infinity. And what happens as t gets arbitrarily large, the log function gets arbitrarily large. This is simply 0, so this is infinite. That integral fails to converge. We saw that in our section on improper integrals. So this integral converges, and I mean, at least graphically now, I have shown you that the harmonic series, here it is, these things here are larger, I mean, than the graph. The area under all these rectangles is larger than the area under the graph y equals 1 over x when I start at 1 and go to infinity. Therefore, the sum of n equals 1 to infinity of 1 over n is greater than the integral from 1 to infinity over dx over x, and therefore it also diverges. A really important result. Okay, it's like things that the things that go to 0 faster than the harmonic series will converge, and the things that go to the harmonic series plus anything that goes to 0 slower than the harmonic series will also um, will also diverge. It's this line in the sand. Okay, And you'll notice actually, just reflecting back on our some of the previous things we've seen, the oddities that we've seen, you will recall that we had the Torricelli trumpet, and that was we had started at 1, and we took this line like that, and we had the function, we had this function y equals 1 over x, and we decided to rotate it around like that, and look at the volume and the surface area. We got some really kind of interesting results. So this is an important function. Okay, so let us make another note of this. The harmonic series diverges. Okay. There's other ways of showing this, of course. I believe that you saw in a previous lecture that you can show that the partial sums grow without bound, and that's also another way of showing that the harmonic series diverges. Okay, so here's a little maybe more formal look at what we've been doing, the integral test. Suppose f is a continuous positive decreasing function. Okay, let a n be f at n. So what we're saying is we've got an integral, let's see, like this. We've got an integral from 1 to infinity of f of x dx, and then we consider the series, the sum, n equals 1 to infinity, uh, being the f at n. Okay, so we're just basically considering the the integral and then the exact same infinite series where we evaluate the function, the same function, but here we just evaluate it at the positive integers. Okay, then this thing over here is convergent if and only if this thing is convergent. And that means it goes the other way. So if this one's convergent, then this one's convergent as well. So that's the if and only if. It's both ways. So I think that's stated here, actually. We have the if the integral is convergent, then the infinite series is convergent. Well, we have it, if the integral is divergent, then the infinite series is divergent. Okay. All right, let's see how we could use this. We get a series that looks like this. It is the infinite series from 2 to infinity of 1 over n times log n squared. Does that go to 0 fast enough or not? That is really, in some sense, the question. It's hard to see, in fact, because we know 1 over n. So what I'm thinking in my head is, what do I know? What does my experience tell me? From 1 to infinity of 1 over n diverges. And then I've also seen that the sum n equals 1 to infinity of 1 over n squared converges. Okay, and then I'm thinking, log of n or log of n squared doesn't grow as fast as n. So we're somewhere in between. And I don't know actually where we're at. So one thing to then do is to consider the equivalent integral. So we basically consider this integral here. We take the integral from 2 to infinity of dx over x ln x squared. Okay, and we're going to see what happens with that. And then we're going to use the convergence of this integral because we can apply our calculus to this because we've got a continuous function. And we're gonna determine that, and then we're going to use that information to determine whether the series converges. That's what this is called, the integral test, because we're using the integrals to do it. Okay, in order to integrate this, we have to make a substitution. So I'm going to make the following substitution. U equals log x. And that means that du will be 1 over x dx. And then I will write out this integral, the limit as t goes to infinity of 2 to t of dx over x log x squared. That's going to be making the substitution now, the limit as t goes to infinity of the integral from log 2 to log t. Substitute, when I make a complete substitution, make sure to substitute the limits as well as the integrand, which will now be 1 over u squared du. Okay, because dx is 1 over x dx. Okay, and then I can easily integrate that. That's going to be the limit as t goes to infinity. And the integral of 1 over u squared is minus 1 over u. And I'm going to evaluate that at log 2 and at log t. Because I've done a complete substitution, there is no need to back substitute. There. That is going to be the limit as t goes to infinity of minus 1 over log t plus 1 over log 2. And then you can see that as t gets large, the log t gets very large. That thing goes to 0, and we get here 1 over log 2. So we have a value for the integral. So we use that value, and we say, therefore, the series converges. The series converges. Okay, and if you're on a test, it would be, nice, not necessarily always required, but you want to point the person to what your thought process is. So you would say, therefore, the series converges, and then you would indicate by the integral test. And then all your prior work is like, oh, I see what they were doing. They were setting up. They showed the interval converge. Now they've claimed that the series converges by the integral test. Okay, let's do another one. We're gonna take a look at the integral test to test out the p series. We call this the p series, and that's, we typically denote the exponent on n by p. We want to know for which values of p does this series converge. Okay, so I'm going to just establish this result using the equivalent integral, and we've already done this. So this, again, if you don't recall, this result is an important result. Check back to the section on improper integrals where we showed this result. So we're taking a look at this integral right here, and we established that it was convergent if p is greater than 1, and divergent if p was less than or equal to 1. Okay, then that's it. We're done because we have this integral test result. So we can, therefore, p series on this sum n equals 1 to infinity of 1 over n to the p is convergent if p is bigger than 1, and divergent p less than or equal to 1. Okay. Again, in fact, p is equal to 1. When p here, let us just, again, hammer home this point at risk of repeating myself endlessly. Look what happens when p is equal to 1. We are here. It's divergent. The harmonic series is divergent. Divergent. Sorry about that. I hit something on my keyboard. Uh-oh. Hang on. Let me escape from that. Divergent if p equals to 1. And that is, goodness. Okay, come on, man. I have some problem with, some problem here with the keyboard. Let me try again. P equals 1. Why is it going away? Okay, hang on. Let me just try up here. P equals 1. Divergent. Okay, there's a ghost writing behind me. Okay, hang on a sec. I am going to go somewhere else here. I'm not sure. I'm not sure why it's not allowing me to write there. Maybe over here. Let's try that. I'm still trying to look at this exponent here. If p equals 1, that implies divergent. And p equals 1 means harmonic series. Okay, so there we have it again. The harmonic series diverges. Ooh, okay. Okay, let us now take a look at what the remainder estimate is. Okay, so we're in a situation where where we have the sum from 1 to infinity of our infinite series. We're labeling that S, and we're assuming at this point it's convergent. Okay. Then we're going to define the nth remainder. Okay, so the nth remainder is the full sum minus the nth partial sum. And it's all the ones that we basically left out. Let's just give an example of this. Let us just look at what S is written out sort of longhand notation. The sum of the infinite series is when we add them all together, A1 plus A2 plus A3 plus A4 plus dot dot dot. That is the exact sum of our infinite series. For example, S3 would be the third partial sum, and we would add together the first three elements. And then, of course, how much would we be wrong by if we said, well, we can't obviously add them all up all the way to infinity. We're just going to make an approximation. We're going to stop after 3 terms. Then what would our error be? Our error would be this amount here, all these ones. That would be our error. And stopping at the third partial sum. So that's what we're calling here R3. R3 would be the real sum, the actual accurate sum, minus S3. Okay, and then you can see why this is n minus 1, because the first one missing here is A4, which is 3 plus 1. This is the case when n equals to 3. Okay, so you can see how the sort of indexing comes about. We have n there, and then we have n on the partial sum, and then we have n plus 1 being the first term that's omitted. Okay, so here's our remainder estimate. Suppose we have a function, f of k is ak, where our function is continuous. So we're evaluating this function at the positive integers, and f is a continuous positive decreasing function, and the sum is convergent. If we define this remainder in this manner, as we just did above, then the integral, that remainder that we're talking about, like how much is our error, it is bounded above by this amount, and it is bounded below by this amount. This is quite an important feature because it allows us to say, well, you know what, we're going to take the first 100 terms. We don't know exactly what the number is, but let us just add up, especially with a computer, for example. We'll add up the first 100 or the first 1,000 terms, and then we want to tell you how much are we out by. And then that gives us a bound on how much error. So you can imagine, for example, in the calculator model, you would only have to go adding up as many terms until you got 8 decimal places of accuracy, and then you just show that to the person in their calculator window, and they have no way of knowing what the actual number is. 8 decimal places is what they see, and so long as you're correct to those 8 decimal places, you are showing them something correct. So we want to be able to provide an upper and a lower bound on the error when we decide to report a partial sum. How much are we out by from the exact answer? So, and maybe an example would be to if you were to ask me, how much money do you have in your bank account? Then I would want to answer some number, and I would want to give an upper and a lower bound. So, for example, I might say to you, oh, I have $1,000 in my bank account with an upper bound of $1,010 and a lower bound of $500. So I just said, I have 1,000. I'm telling you, my estimate of my bank account balance is $1,000, and I'm telling you that I don't have more than I forgot what I said. Let us just say I said $1,010, and I for sure at least have $500. So I don't have as much certainty on the lower end as I do on the other end, but that is telling you that my best guess of what I have in my bank account is $1,000, and for sure I'm guaranteeing you that I have between $500 and $1,010. We want to do exactly the same thing. We're going to take the error in evaluating our sums. What is the difference between what we told you and what the actual answer is, and we want to bound it above and below. Why does this work? We can see graphically why this works. Okay, here is the integral. Here is the integral from this red line here. This is the integral from n to infinity of f of x dx. And a of n plus 1 is sitting right here underneath the curve. So you can see that this integral is an upper bound on the on the things that are missing. So these are this right here. If I add all these together, this gives me Rn, right? This is the area here. The area is equal to Rn, like, because it is equal to An plus 1 plus An plus 2 plus dot dot dot, and that's exactly what we saw was Rn. So that integral gives me an upper bound, and similarly, getting it here on the same page, let me just shrink it a little bit so we can see them both. Similarly, if I sort of take all these rectangles and shift them over by 1, I end up with here, and I say, oh, actually, my error that I've incurred, same thing, I just add these all up. I can see that that's actually bigger than this, the area under this thing, which is the integral from n plus 1 to infinity of f of x dx. Okay, so by using two different integrals, I can give you a bound on the error when I leave out some number of terms. That is what we have called the remainder estimate for the integral test. Okay, so we had a example we just did right here. Here it is. We showed that it converged. That's all we did. Let me tell you that, for example, you could try this out yourself. You could put in a huge number of terms. You could, for example, in a computer, you could fairly easily program a computer, and you could say, make this calculation. The sum of n equals 2 to 100,000 or something like that, and allow it to run for a little bit and then give you a number. That's a possibility. And you would get some number out. I cannot remember when I did this what number I put here, but let me tell you that I got an approximation for this sum by taking a lot of terms to be this here, 0974. Okay, so that's just an approximation. Okay, so what we now want to answer is, how many terms would we need to find the value accurate to within 0.01? Like, how much do you have to add? How many terms do you have to add to get the remainder to satisfy this inequality, Rn less than 0.01? Okay, so I have here Rn is less than or equal to the integral from n to infinity of f of x dx, and that's we want that to be less than 0.01. Okay, inequalities are quite tricky. Make sure that you line up things in the correct direction. So that means I'm going to need to evaluate this integral, and that's fine. We did this already, in fact. So let me just we just did this. But let me just reiterate from n, because we actually went from 2 last time. So we want to take this integral, because we're going here, the bottom, the lower limit of integration is n. It's the exact same integral though, so of course the process will be exactly the same. Okay, there it is. That's the integral, and so that will be 1 over log n. That's from before. Last time it was 1 over log 2, but that's because n was 2. Okay, so that was from earlier. You can scroll back if you need to on that. Okay, so that means we need this integral to be less than the value of the integral, which we've now just determined. We need it to be less than 0.01. That means that log n will have to be greater than 100. Remember, if you take the reciprocal on both sides of an inequality, you have to change the direction of the inequality. So I've took the reciprocal on both sides, and I changed the direction of the inequality. Okay, now that means that n is going to have to be greater than e to the 100. It's huge, huge, huge. Okay, it converges very slowly. This converges very, very slowly. So I did actually make a couple of other calculations. Maybe I got the exact value from a table. It's looking like I probably didn't do that many calculations. So if I did this, this is the series we're talking about. Sorry, I'm not going to do it to infinity. If you do 100 terms, I did manage to get this number, approximately 1.8928. And then when I did it to 1,000, same thing, but I took this would be the thousandths partial sum. So I would call this S 1000, and I would call this S 100. the hundredth partial sum, the thousandth partial sum, and I got, when I did that, 1.964, and then if you go to 10,000 of the same thing, I got approximately 2.0011. So it's extremely slowly converging series. Okay, so what we've seen here is how to use an integral to find whether a series converges or not, and also to use an integral to bound above or below what the series converges for, also to provide an error estimate. The topic of convergence and how quickly something converges and how fast you can get numeric approximations, especially in this age of computers, is an extremely interesting and a very valuable topic of study. Thank you. The next lecture will be Jessica Stockdale on section 11.4. Thank you. Bye-bye.